Now let's look at an application of the Erlang B formula. We want to dimension a telephone network over a certain region. In other words, we want to determine the number of lines that are needed in a telephone exchange or switching station. We assume that calls arrive according to a Poisson process with a rate of 1 call per minute on average. We also assume that call durations are random and exponentially distributed, and on average, they last 3 minutes. Our problem is to determine the number of phone lines to install in order to guarantee that the blocking probability is going to be lower than 1%. In order to do so, we note that, thanks to the Poissonian arrivals and exponentially distributed call durations, we can model the system as an MMCC system where the parameters are lambda equal to 1 call per minute and mu equal to 1 divided by 3 minutes to the minus 1. So we have an offered load which is equal to 3 Erlang. Our problem boils down to finding the value of C such that the blocking probability given by Erlang's formula is smaller than or equal to 0.01. But we can see that using this formula can be rather cumbersome, so we'll use a graphic method instead. In this graph, we can see the blocking probability as a function of the load of the system for several values of C in a logarithmic scale. We know that we are working at a load which is equal to 3 Erlang, that is 3 times 10 exponent 0, and that we need a blocking probability of less than 1%, that is less than 10 to the exponent minus 2. We then look at the intersections of our working load with the different curves for different values of C, and look for the intersection where the blocking probability is immediately below the red line. So we keep the solution of 8 servers, which provides a blocking probability around 0.8%. Another highly used method are pre-calculated tables. In these tables, we have the supported load for different system capacities and blocking probabilities. 1% in this case. In our problem, we need to support at least 3 Erlang with a blocking probability of 1%. So we see that we need at least 8 servers, and we find the same answer as before, namely that we need to install 8 phone lines.